I will start the tight binding method. So it's a method for band structure calculation, and it's a method that is starting from another extreme with respect to the plane wave method or the quasi-free electron method that we have seen before. Here we start from atomic type of states. So the plane wave will have probability which were uniform and homogeneous. So for the delocalized type of valence state. And the approach we are using now will be a linear combination of atomic orbital or orbital of ions, also this is possible. So we start from basis functions that are very localized in space, that have a probability density that is around the atom. So it's another extreme, and this approach is good in particular to describe semi-core states, because they are close to what are their wave function in the atom, and also for carbon system or for ionic system, ionic insulators, where the states are close to those of the ions. So this is the method we will see today and until the next lectures. So the tight binding method calculate band structures or tight binding model. It's an approximation. It's also, so the solid state physicists call it the tight binding method, and in chemistry it's known as the LCAO method, the linear combination of atomic orbital. So LCAO for the chemist, which is the linear combination of atomic orbitals. Okay, so we will, as is indicated here, use states that are linear combination of atomic orbitals. So the solution or the states we will consider for the electron, the psi of R, the solution in the end will be in the form of a sum over the Lattice vectors, or the vectors that bring to each unit cell in the crystal, phen mu, which is the atoms in the basis. So a crystal structure is Bravais lattice plus a basis, so we sum over the vector of the Bravais lattice and over the atoms in the basis. And we sum phen for each atom over the orbital of that atom. So S orbital, 1s, 2s, 2p, and so on. So I represents the type of orbital for a given atom. And then we have a coefficient, alpha, which depends on R, mu, and I. So we sum over all these indexes. And then we have the atomic orbital for the atom mu and the orbital type I, so 1s, 2s, and so on. So these are the atomic orbitals that are centered on an atom mu that is in the cell R. So we sum the atomic orbital over each atom in the crystal. the position of each atom in the crystal is given by the Bravais lattice point plus the vector that brings to that specific atom in the unit cell. Okay? So this is, in general, the way we will write the crystal state. And here, phi mu I atom are the solution of the atomic problem. So phi mu I are the atomic solution that is that they verify the Schrödinger equation for the atom, so minus h bar square over 2m Laplacian plus the atomic potential for the atom mu at the origin, phi mu I atomic of R is equal to epsilon mu I. This is the atomic energy for the atom mu and the orbital I, phi mu I of R. Okay, so this just states that this phi mu I are the solution in the atom. Okay? All right. And then in the tight binding method, the other thing we do is we write the crystal potential as a sum of the atomic potential. So the crystal potential in the tight binding approach is written as a sum of atomic potential. So for the potential for the atom mu of R minus the mu minus capital R. So the crystal potential is written as a sum of all the atomic potentials centered each on the atom in the crystal. Okay? So this is what the tight binding method uses as basis and as assumption. Crystal potential written as a sum of atomic potential, and the state in the crystal written as a linear combination of atomic states. It could be also ionic state, but here I'm just going to discuss it in the case of neutral atom, solution of the neutral atom. For the ionic case, it's similar, just one uses the wave function of the ion. If it's sodium chloride, one would use the solution for the ion. Okay. So now let me show a plot of what are the states we are using and what we will do then as approximation. The first type of approximation we will make. So if I write, or if I plot, I'm assuming I have a monoatomic crystal, so I just sum over the Bravais lattice vectors. All the atoms are of the same type, I don't know, carbon, and it's a monoatomic crystal, so the atoms are on the site of the Bravais lattice. So if I plot in the crystal in R space the potential V of R. I have my atoms on I go along a line that goes through a row of atoms as usual, and if I consider the atomic potential V atoms centered on each of the atoms, I have a Coulomb type of potential, let's say. Do this a bit further down, show better things. Okay, so I have a potential that goes like this. This is the Coulomb potential, and I'm summing over the Coulomb potential on each of the atoms. Okay, so these are the Coulomb potential on each of the atoms, and I'm summing these atomic potentials. Okay, so if I consider just, let's say, this potential for this atom that is centered here, I will have for these atoms, let's say the lowest atomic level here, which will be a 1s state. So this is the energy of my 1s state. So this is at the position R of the Bravais lattice, where I have an atom, and I will have the wave function of this atom, of the lowest state of this atom. So this is going to be my phi 1s centered at the site R minus capital R. Or if I do the problem in the atom, I place it at the origin. So this is going to be the wave function at the centered at the origin. So this is my 1s state, and I will have some n equal 2 states. I will have the 2s and the 2p state, px, py, and pz. So my potential here shall be symmetric. So this is the level, energy level of the n equal 2 states. So I will have some p states. Let's see. This would be some p states. So phi 2p, and I have the x, y, z. So 2px, 2py, and 2pz as eigenstate in the atom. And I will have also some s state that will have a node, because so well, okay, let me have this a bit better. I have a level here, so I have some p state here, and I have some s state, let's say, like this. This would be my s state, it will be symmetric. So this would be my phi 2s state. So I have 4 states at this level, which are the atomic state. Well, it's a cartoon, I mean, but just to show that these states, if they are, let's say, semi-core state, they would be very localized. The atomic states would be very localized around the atom. So these are examples of the states I will have in my linear combination of atomic orbitals. So in principle, in the tight binding method, or the way I wrote the wave function at the beginning, I was summing over all lattice side, over all atoms, and all over all atomic orbital of a specific atom. So the initial basis I had was for all the atoms in my crystal. It's a monoatomic. I'm taking here the case of, as an example of a monoatomic crystal or lattice. So, in principle, at the beginning, I was summing over all R, over all atom in the basis, and over all atomic orbital of a specific atom. But this is an overcomplete basis, because in principle, if I sum just for one, or if I take just for one of the atoms, all the orbital with energy going to infinity, so including also the unbound state, I have a complete basis. So here I have an overcomplete basis, which is okay in the sense it doesn't hurt, but it's too much. We don't need all this state. So instead of summing over, taking only over one atom, which would be physically a very bad choice, obviously, we will just focus on the lowest state of all of the atoms. So we will include the 1s state, the 2s and 2p state for carbon, for instance. And for carbon, we would stop there, because we have the states that are relevant for the valence electron of the crystal. So the idea is we use this overcompleteness in order to choose some states that are physically sound for our basis. And we will choose the lowest state of each of the atoms up to a certain point. So up to where depends on what one wants to, what states are relevant, that is, are in the valence and in the lowest conduction bands, basically. Or, so this is the idea. So, as I said, this is an overcomplete basis. So this is an over-complete basis, and we will restrict the state in the basis by taking only a few atomic states. Continue here. Only a few atomic orbitals. And we will choose them as the lowest bound state up to a given energy. So we will choose the lowest bound state up to a given energy, and the choice depends on the system one is considering. One should know more or less what type of valence electron one will have near the gap or near the Fermi energy if it's a metal. So atomic orbitals lowest bound state up to a given energy. Okay, so this is what we will use as a basis. So the consequence, this is an approximation or a choice, and the consequence, since we limit the basis this way, is that the LCO, or the tight binding method, or model will work in the case of state in the crystal that are tightly bound orbitals, so not too much modified by the presence of the other atoms. So this is valid for the semi-core state, core state or semi-core state, obviously, and also for states in ionic crystal, where the states are close to those of the ion that form the crystal. And, for instance, the carbon or element of that line have also very tightly bound orbitals in the atoms, so also in those cases this method works well. So the LCO tight binding or tight binding model will work well in the case of tightly bound to the atom orbitals. So in the case where the states, such states in the atoms, from each atoms in the crystal, are not too much modified by the other atoms. Okay, so far? It seems reasonable. Okay. All right. So now, of course, since I'm a crystal, I'm in a crystal, my my crystal state, have to satisfy Bloch theorem. So they have to have the form of Bloch states. So, the Bloch theorem applies to my CR, my state CR that I wrote as a linear combination of selected atomic orbitals, that is, those up to a certain energy, the lowest state up to a certain energy. So this C state in my crystal, I can label them with a K vector, which is a good quantum number. So Ck of R, and These are Bloch. Have to have the form of Bloch states or Bloch functions. So I first write my orbitals in general. I want them in the form of a linear superposition of atomic orbitals, and then I impose now that this state have to be also Bloch state. So to do that, I will first take the example of a 1s state. I want to write my linear combination of atomic orbitals. So in this case, I sum over all Bravais lattice sites in my crystal some coefficient times the S function centered on that side. So if I take, for instance, the example, the case where I have one atom per cell, so monoatomic lattice, and I consider just one orbital, one type of orbital, which I will take as the 1s state. So one atom per cell, and just the one orbital that is the 1s state. Then, if the Bloch state for k equals 0 is easy. This one can be straightforwardly guessed or obtained. It's just summing over all the atoms in the crystal, in the Bravais lattice, the 1s orbital on each of the atoms. This is the Bloch state with k equal to 0 because it's periodic, since I summed over all the atoms in the crystal. So, constructing a Bloch state in terms of the 1s orbital, for instance, for k equal to 0 is easy. So, for k equal to 0, the Bloch function that would be constructed from that orbital Bloch function from the 1s orbital would be just phi 1s of k equal to 0 r. This is just 1 over the number of cells in the piece of crystal I consider, times the sum over the Bravais lattice vector r phi 1s atomic of r minus capital R. So this is the Bloch state that I can construct for k equal to 0 from my 1s orbital, because this object is periodic. Has the full periodicity of the Bravais lattice. Well, I can also, and I will do it here, just show that it verifies the Bloch's theorem in the second, the second form of the Bloch theorem. So it satisfies Bloch's theorem. And here I will use the second form that we had for the Bloch theorem to give Bloch function. It is that when I translate or I add to my point R a vector of the Bravais lattice, I obtain a wave function, the same wave function times exponential IKR, the vector I use. So one of the forms of Bloch's theorem was that if I add to my vector or to my point, I translate by minus R the wave function. So I add a vector R to capital R here. I obtain exponential I k, and this is 0, times R prime. Sorry. Phi 1s of k equals 0 R for any R belonging to the Bravais lattice. So if maybe not to mix R and R prime, I will put an R prime here. So if I add to my Bloch state and to my state phi R, a vector of the Bravais lattice R prime, I obtain the same wave function times exponential I k R prime. This was the form of Bloch theorem, the second form of Bloch theorem we had seen. So in the specific case of k equal to 0, my function here verifies it. If I add, I translate here by R prime, I can resum over R second prime, that would be R minus R prime, and I would obtain the same object. I can, so this is clear, okay? I mean, it's clear for everybody that is, if I add a vector R prime here of the Bravais lattice, I obtain the same function. Okay, all right. So our Bloch state at k equal to 0, we know how to construct it. And here I took the specific case of a 1s function, but I could do the same with a 2s function, or with a 2px, or with a 2py, or a 2pz function. I would obtain a Bloch state at k equal to 0. I mean, a state that has the Bloch form for k equal to 0. So, for k equal to 0, we know how, and this is obviously a linear combination of the atomic orbitals. So, I know how to do it for k equal to 0. Now, for k different from 0, there is a specific form that satisfies, that is a Bloch state. So now, considering the case for k different from 0, k belonging to the Brillouin zone, but different from 0, the tight binding function has the following form, and this is an ansatz, and finally we show that indeed it satisfies the second form of the Bloch theorem. So I will write it, the tight binding Bloch state, for the atom mu and the orbital I at k point that is non-zero, that I consider non-zero, So my Bloch state, I can write it as 1 over the number, the square root of the number of unit cell, sum over the Bravais lattice vectors, exponential I k times r, phi mu I atomic of r minus d mu minus capital R. So I'm summing over all the unit cell in my Bravais lattice over and for, okay, I'm starting for a specific atom. I want to calculate the tight binding function for the orbital I of a specific atom type like carbon mu. So I want to construct the tight binding function for the carbon 2s states, let's say, at a given k point. So I will sum over all the unit cell the atomic orbital 2s centered on the carbon atom in that unit cell. This is the way I will do it, and then I have this coefficient which is a phase that is exponential ikr. So it's a linear combination of my atomic orbital and the specific coefficient that will give a Bloch state is this phase, exponential ik times r. Okay, so this is an ansatz. I'm telling you that this linear combination of atomic orbital satisfies Bloch theorem. And we will show that it satisfies the second form of Bloch theorem. So I will just calculate phi mu I of r plus a vector r prime that belongs to the Bravais lattice of my crystal. So if I do that using my ansatz here, I will get 1 over the square root of n, sum over r, exponential I k r, times my atomic function for the choice of my basis, that is mu I, at the position r minus d mu minus r, and then I added the r prime here. So this is just adding, translating the wave function. And this so this object, I continue here, and I will use now a change of variable. So I will call this r minus r prime, I will call it r second prime. So I will call r second prime the quantity r minus r prime. So I change variable and use r second prime as this difference, and this way I'm obtaining 1 over the square root of n, sum over r second prime change variable, exponential I k, and here I have r, so it's r second prime plus r prime, so r prime plus r second prime. And then I have my atomic function here, and now it is at r minus d mu minus r second prime. Okay, just change variable, and this is what I'm obtaining. And as usual, we assume that over n units of my crystal, I have the periodic boundary conditions, so I can always, this sum is over the same number of vector here, and it's the infinite sum of over the reciprocal lattice vectors. Okay, so this is equal now to exponential I k times r prime times what remains is the sum over r second prime exponential I k r second prime times my atomic function in the cell r second prime, and this is exactly my initial state. So this is just phi mu I of k r. So indeed, my state written this way as linear combination with of this atomic orbital with this phase as coefficient is a Bloch state. It satisfies the second form of Bloch theorem. So this is the way that I can obtain a Bloch state as linear combination of a type of atomic orbital. Okay? All right. Okay, so now we know how to write the Bloch state in general for any k, and of course for k equal to 0 we recover what we guessed initially, that is it's just the sum with a coefficient 1 of the atomic orbital.
Excuse me.
Yes?
When we said our full eigenstates, the basis states were over complete,
Yes.
our logic was that at 1r the different orbitals is enough to expand the
Yeah,
space.
for one atom, if one uses all the states going to energy infinity, then one has
so it's
already...
not necessary to go through the Bravais lattice. But rather than putting a limit on r, we are now putting the limit on I, different orbitals. Because by this logic, we should normally put a limit on r, let's say 1r or few r's, and go through all the orbitals. But rather than doing that, we are going through all the r and putting a limit to I.
Yeah, to the energy.
So
instead of, but it makes sense.
Is it still complete this way, going through all the r rather than? In what way, ma'am? Because
it's not complete, but it's a good approximation for knowing the physics of the system. Of course, if this way you want to describe a free electron system or free electron-like metal, you are in trouble, because you should sum over all the atoms, since this is what we do in this method, but you will have to use very large energies to get something that is reasonable to describe a free electron state. So this works well, knowing what will be the final, let's say, type of electronic state we will have in our crystal. If I know, if I was applying this to a sodium crystal, I would be in trouble because I know the state should be free electron-like. So I will obviously need to include some unbound state to get something that will then give me again a free electron type state. So it works only for certain kind of systems, crystals. It's the opposite. It's in some sense the other limit with respect to the free electron model or the plane wave approach that we used before. With the plane wave approach, one could also describe a system, a semi-core state. But one would need such a huge basis of plane wave in order to be able to describe some localized state. Huge Fourier, G vectors, in order to be able to describe an atomic state. So this would be crazy and a waste of computer resources, because one would need a basis that would be huge. Here it's the same thing. This will work only in system where the charge density is localized close to the atom. Inhomogeneous and with the probability largest near the atoms. So this is complementary to the other method. It depends on what you want to do, because again, one could also describe the other system, but with a basis that would be huge. So the goal is just to describe with a few orbitals per atom some system where we know that this is close to the result in the crystal, or close to the state in the crystal. Okay? All right, so now I have shown that this satisfies Bloch theorem. So now I want to present some example. Just let's consider a system with one atom per cell, one electron per cell. One atom per cell. So take, for instance, a system with one atom per cell, and I will consider the atomic orbital in my basis. The 1s, the 2s, the 2px, 2py, phi 2py, and phi 2pz. So I consider these 5 atomic orbitals. For instance, I would have a carbon atom, and I consider the 1s, 2s, and the 2p state of carbon. So I have 5 atomic function per atom, and for each k, I will have 5 tight binding functions that I can use as a basis. 5 tight binding functions. And these 5 tight binding functions will be so P1s, but I can do the same for 2s, 2px, 2py, and 2pz. Well, 2p alpha, let's simplify. Okay, so for 2p alpha, where alpha is x, y, and z, so I can construct my tight binding function phi k of r using the specific orbital 1s, but I can do all the same for 2s and for the 2p alpha atomic orbitals. So this is going to be 1 over the square root of n, number of unit cells, times the sum over the lattice vectors I k times r. This is my phase. And then I have the atomic function phi1s, for instance, centered at r minus capital R. So I have my, it's 1 atom per cell. So I put the atoms on the lattice point R, and I'm summing the 1s function centered on each of the atoms at the lattice site times this phase that is the coefficient in my linear combination of these atomic orbitals. So I can do it for the 1s function, but I couldn't do the same for the 2s and for the 2p alpha. So I obtain 5 basis function, tight binding basis function from these 5 orbitals, which have the block form. Of course, if my basis has the block form, then any state I expand as a linear combination of this basis function will also be a Bloch state. So if I have this 5 Bloch state, and then I write my crystal state as a linear combination of this 5 Bloch state, it will also be a Bloch state for the same k, obviously from the form it has. So I needed to do this in order to have for my crystal state that I will then expand on this Bloch basis function, tight binding Bloch basis function. I will have the correct form for my crystal state. All right, so for each k, I have in this specific example 5 tight binding functions that are in the Bloch form. So it's in the specific case here, it's not a complete basis, but it's a very good approximation for a system formed by carbon atoms, for instance. And if I wanted to improve, I could use higher n orbitals. So I can always improve it, but this is the minimal basis that will give me a physically sound result. Okay, so it's not a complete basis. So it's not a complete basis. One can construct a complete basis by taking or considering all NL states, but these 5 orbitals are good enough. For the lowest energy state. Good enough for the lowest. Eigenstates. In the crystal. Of course, how many one includes will depend on the system. Here it's the case of carbon, so I will go up to these 5 orbitals. Okay, so now that we have Bloch states from linear combination of atomic orbitals, we need to apply, impose Schrödinger's equation to get the crystal states. So this is the next step. So at a given K, now I need to solve Hc is equal, so H psi k is equal to epsilon k psi k. So I need to solve the Schrödinger equation. So I will solve this by using my tight binding basis. The tight binding function. So I will use as a basis my function psi k r 1 over n sum over r exponential I k r times my atomic function mu I of r minus d mu minus r. So I will need to solve this using as a basis this function. So in the case of carbon, I would have 5 functions here. In another case, I could have more than one atom per unit cell, or in the basis, I could have a boron and a nitrogen atom, for instance, and then I would have the orbitals of this atom. In that case, one would also use a limited basis corresponding to this type of states. So this is in general, the basis has this form. And now So here I will include the lowest energy atomic state, so this is for the lowest energy atomic state, I equal 1 to n. So I'm writing in general, and one tries to use the minimum number of n possible that gives a physically accurate result. So my basis is this. And now I need to solve the Schrödinger equation using this basis to expand my crystal state. So the Hamiltonian, as I mentioned, that I will use is has as potential as sum of the atomic potential. So my Hamiltonian, my crystal Hamiltonian is h bar square Laplacian over 2m, the kinetic part, plus the sum over the unit cell and the atoms in the unit cell, V atomic of mu of centered at the position of the atoms, mu in the unit cell R. So this is my crystal Hamiltonian written with the potential written as a sum of the atomic potential. Okay? So now, as I mentioned, I will write my crystal state, C K of R, as an expansion on my basis function. So I will sum over mu and I, a coefficient A mu I, phi mu I. So these are my type binding basis function for the k point k, and this is a function of R. So I'm writing the solution for my crystal Hamiltonian as an expansion on the basis function, which are this function. Okay? So, as I mentioned, this has the block form, and therefore this has also the block form, because it has the same sum over it has the form. One can apply the second form of Bloch's theorem on each of the components of the sum here, and one obtains this phase exponential I k times the vector that was used for the translation. Okay, so this is the solution, and now we will do like we did in the case of the plane wave basis. We want to obtain for the solution also an eigenvector matrix eigenvalue eigenvector equation to solve. So we want to solve this. HCk is equal to epsilon k phi k, with the phi k written in this way, and we will use exactly what we have done for the plane wave problem in order to obtain an eigenvalue, eigenvector matrix equation. So what I will do is here I am writing the psi in this form, and then I will multiply by the complex conjugate of a basis function psi mu prime I prime, and I will integrate. So I will do like in the case of the plane wave basis, I will multiply by the complex conjugate of the basis function mu prime I prime for the same k. And I will multiply then this, the complex conjugate of this basis function, times the Hamiltonian acting on my function k. So it's sum over mu I, a mu I, phi mu I of k r. And on the other side, I obtain epsilon k psi mu prime I prime of k r sum over mu I a mu I of psi mu I of k r. Okay, so I just use this equation and I multiplied by the complex conjugate of a basis function phi mu prime I prime, and I integrated over space. I'm doing this on both sides, and this is what I get, okay? So now I can rewrite this as sum. I can take out the sum over mu I, and I have phi mu prime I prime of k r h phi mu I of k r. The coefficient a mu I is equal to epsilon k sum over mu I phi k r. This is mu prime I prime and phi mu I k r. Okay, and then I need the coefficients a mu I. Okay. So this is the equation I get in the end from this equation here. I'm summing the matrix element of the Hamiltonian over my basis function of the Hamiltonian times the coefficient epsilon k, the eigenvalue, times this overlap matrix times the coefficient A. So again, I obtain a matrix eigenvalue eigenvector system, equation system. In the difference with respect to the plane wave case is that we have here also an overlap matrix. So we have to solve a problem of if these are the matrix element of the matrix H, I will have to solve something of that type is equal to epsilon times, let's say, an overlap matrix, which would be the matrix with these elements, times the vector A. In the case of the plane wave, we had the unitary matrix here, and here we have in principle a matrix that is different from the unitary matrix. So it's a more generalized eigenvalue eigenvector problem that one has to solve. Okay, yeah, everything. All right, so now we will try to simplify this matrix, calculate this matrix element and obtain something a bit more simpler and the initial expression. So on both sides I have matrix elements to calculate which are of the type the basis function, type binding basis function mu prime I prime kr, an operator which is periodic, and a basis function mu I So on both sides, the matrix element that I have are of that type where the operator is a periodic, that is, has the periodicity of the Bravais lattice. So it's valid for the Hamiltonian and it's valid for the constant here that I have. In both cases, I have to evaluate something of that type. Okay? So this actually, if I do, I replace my type binding function by the explicit expression. I'm getting 1 over n, sum over r prime and r. I have a double sum, exponential minus I k times r prime minus r, and then the matrix element of the atomic functions. So the atomic function mu prime I prime centered on the atom mu prime in the unit cell r prime. My periodic operator, and here I have the function, atomic function phi mu I centered on the atom mu in the unit cell R. Okay, so this is just using the explicit expression for the type binding basis function. So this is what my matrix element is. Now this actually depends only on r minus r prime. So this is the same as this is the same as phi mu prime I prime of R minus d mu prime. My periodic operator phi mu I of R minus d mu minus R plus R prime. Given that this is a periodic operator, if I change variable and I'm adding the vector R prime in every part, I will obtain here this function of R minus d mu, this function of R minus d mu minus R plus R prime, and since this is periodic, I will not change it by adding the R prime. So this matrix element is the same from this one. Do you agree it's okay? This comes from the periodicity of the operator I have here. So if I change variable and I use as integration variable R prime, that would be R minus R prime, capital R prime, I will obtain this as a result. Okay, because O is periodic. So if I add a Bravais lattice vector to O, or if I translate using the Bravais lattice vector R prime, I will not change my operator, it's remaining invariant. Okay, so fun, things simply fun, because this well, I can change variable. So then I can use R second prime is equal to R minus R prime. And I'm obtaining 1 over n, if I do things explicitly, sum over R, sum over R second prime, exponential I k R second prime. Okay, I'm going with collision. Phi mu prime I prime of R minus d mu prime. My operator, phi mu I of R minus d mu minus R second prime. So I just rewrote the whole thing, but this doesn't depend anymore on R. So basically I'm summing R n times the same thing, because this depends only on R second prime, doesn't depend anymore on R. So I can simplify this, because I'm summing n times the same thing. And all right, I'm continuing on the other side of the blackboard. So this is the matrix element, and this is equal. Well, I can stop here. So basically, I simplified this, and the end result is just the sum of the phase times this matrix element. So because of the periodicity of the operator, I can simplify the double sum into just a simple sum, single sum over the lattice vectors. So this is what this matrix element gives, and now I'm going to use it both for the overlap and for the matrix element of the Hamiltonian. So my matrix element phi mu prime I prime of K R H phi mu I of K R. Because of this, I can write them as a single sum over the lattice vector I K R phi mu prime I prime of R minus d mu prime H phi mu I of R minus d mu minus capital R. So here I just used what I obtained here. All right. Okay. And now we will use the fact that the Hamiltonian is sum over the atomic potential. I mean, the crystal potential is the sum over the atomic potential. So here, my Hamiltonian, I will write it in some special way. That is, okay, I will write the kinetic part. This one, I leave it as it is. So h bar square Laplacian over 2m for the kinetic part. Then the crystal potential, which is a sum of atomic potential, I will write it as the atomic potential of the atom mu prime at the site, at the position r minus d mu prime. So, and I will sum and subtract the same thing. So I will write the crystal potential, and then I will subtract this, the V atomic of mu prime of R minus D mu prime. So my Hamiltonian, I wrote it as the crystal potential, the kinetic part, and then I have added and subtracted the same thing. And what I have added here is the atomic potential for the atom mu prime centered on the atom mu prime in the cell near the origin. So in the cell that it's a Wigner-side cell centered around the origin, I put here the atomic potential that corresponds to this atomic state. So I center it at the same place because the idea is that this is the atomic Hamiltonian, and I know that this is an eigenstate of the atomic Hamiltonian. So that's why I'm writing my crystal potential this way. And this, so this part is just the Hamiltonian, the atomic Hamiltonian for the atom mu prime, centered on the atom mu prime that is in the cell corresponding to the origin, labeled by the Bravais lattice vector at the origin. And this part, I will call it V prime. I will label it V prime, and I will call it the crystal field. So it's the crystal potential, which is a superposition of atomic potential, and I remove the potential of due to the atom that is in the unit cell near the origin. So the idea is that I want at this site to have the effect of the potential of all the other atoms except the atom where I sit. So it's the effect of it's the crystal field that is for this atom. This is the effect of the potential of all of the other atoms, but one doesn't include the self effect, so it wants to have the effect just of the neighboring part of the crystal. I mean, of all the atom around itself without counting itself. Is it clear?
Yes.
It's the crystal definition of the crystal field. So now, having written things this way, I can obtain some simplification. So this is going to be equal, because my Hamiltonian is Hermitian, or it's self-adjunct, so I can translate, I may put it on the other side, and here I will have the eigenvalue epsilon mu prime I prime, the atomic eigenvalue. So now this is going to be equal to the sum over R exponential I K R, and then I have, as I mentioned, using the first part here of my Hamiltonian, I will obtain the atomic eigenenergy, epsilon atomic for the atom mu prime I prime, and then here I have the matrix element phi mu prime I prime of R minus d mu prime phi mu I, and this is at the site d mu, but in the unit cell R. So this is the first part, the atomic energy times this matrix element between the atomic orbital, but centered in principle on two different sites atoms. And then the second part that comes from the crystal field will give me the matrix element mu prime I prime of R minus d mu prime crystal field d prime of R phi mu I of R minus d mu minus capital R. Okay. All right. Okay. So now I can rewrite this as epsilon mu prime I prime atomic, because this with this phase times this is exactly what I obtain for the matrix element between the two tight binding functions. So here I have epsilon atomic, and what remains here is the matrix, the overlap between my tight binding function, basis function, mu I of A R, plus, and the other part doesn't simplify, it's a sum over R exponential I k R phi mu prime I prime of R minus d mu prime and the crystal field phi mu I of R minus d mu minus capital R. Voilà. So this is what we get for this matrix element between the Bloch, the tight binding basis function. So basically I obtain first the atomic energy and the overlap between the basis function, and then I obtain the second part where I have to sum over the gravilattice vector. So just to summarize for next time, what I obtain in the end, and I can simplify considerably my problem this way, is for the equation I will have to solve. So I will have to solve in matrix form, and this equation H for a given k, I will have the matrix element of mu prime I prime mu I a mu I. So this is all for a given k, epsilon k, sum over mu I. I call it A, the overlap matrix here. So it's also for a given k in principle, mu prime I prime mu I a mu I. So this is my eigenvalue eigenvector equation. The H here this is a matrix that has, on the left hand side one has mu prime I prime, and on the right hand side mu I. And this matrix is the atomic energy mu prime I prime for the atom mu prime and orbital I prime. Then there is the matrix element here of mu prime I prime, the tight binding function R phi mu I of k R. So this is the first part, and the second part is something I will call T mu prime I prime mu I of k. And this T is just this sum over the lattice vectors of matrix element involving the crystal field. So the T mu prime I prime mu I, and also dependent K, is the sum over the lattice vector exponential I K R, and then I have here mu prime I prime of R minus d mu prime, the crystal field, so this is the expression for the T, and this T we will call them the Hoping terms. And then finally the A are the overlap matrix. This is the overlap matrix. So the matrix element are given by this. Mu, so this is prime, and this is the prime. And so this is the overlap term. The overlap term. So I have this equation to solve, which is an eigenvalue, eigenvector matrix equation to solve, and the matrix element for H and for A are given here, and for the Hamiltonian is just the atomic energy times the overlap matrix, and then there is this additional term that we call the Hoping term, that is the sum here of exponential IKR over the lattice vector R of the matrix element of the crystal field. And okay, this is what we will have to solve. And I will stop here, and next time we will start from there and do some approximation to calculate this type of, and solve this type of problem. Okay, any question? It's clear?
Next time we'll have...
Next time there will be the tutorial,
So then
next
exam.
Well, yes, it will be next time there is the course. So next on Thursday there will be the tutorial, and on Monday the midterm. So at the normal time.